What'd you get, guys? I'll put it up here. 81? 56? 89? Interesting. All right. No, nothing wrong. All right. All right, guys. So, looking at the intervals, don't worry about these yet. What does it look like? And I know there's only 3 of the dudes, but if you compare the intervals, who looks like, would the women's average be higher than the men's or vice versa? Let's see if you guys can tell. If only there were more men samples. Yeah, they're pretty close, right? Although there are a few more women's that are 70s and 60s. You see that? So it looks like there might be evidence that the males are slightly higher.
Yeah, because you crossed out the 80 as an X on that one, and the 80 was.
Don't worry about the X. Don't worry about that.
I was like, well, yeah.
So that last question on the handout, that is the actual average of all those numbers up there, right? So for the men, it was 81.22. So if your confidence interval didn't catch that, does that mean you made a mistake? No. Because how do we build a confidence interval around a sample mean? And if we randomly select a lot of low scores or a lot of high scores, won't that move the interval possibly for, it won't catch the real mean then? So what do I say, when I say 90% confident, that means that what percentage would I expect to not catch the mean? 10%. And there were 12 groups. 10% of 12 is 1.2. So on average, I would expect 1.2, on average. And we had 3 that didn't catch it. So that's a little higher than average, but not outside the expected if I did that whole work. You guys semi with me here? So if I had, 25 groups, it would have been a little bit better. Normally, the bigger groups, the more almost exact it is, which is really nice to see. If I would have seen like 8 that didn't catch it, I would be like, what the hell happened? Something happened. Something bad. Did everybody, what was your T-score you got?
1.729.
Yes. So if anybody did not use that, that's one mistake. I like it. Okay. So what do the X's mean? They're the ones that didn't catch the real mean. That's all. It doesn't mean you did something wrong. That's the beauty about statistics. This isn't exactly, you can't, did I wear that shirt? Good. I was like, did I put the shirt on that I thought I did? Am I pointing to something weird? Statistics means never having to say you're certain, because statistics is the most honest math. It says there's always a chance I'm wrong. But I want to get a feel for something. I mean, if I'm like, okay, I got to choose which way to go, I'd like to know the probability I live, like I'm trying to run out of somewhere. For some reason, I think about that stupid movie 2012 with we're like, which way do I go? The ground is going, the fire's coming. Which way do I go? Well, we got a 70% chance of living that way, and it's 60%. Oh, okay, I'll go that way. Does that mean you will definitely live? No. But it's an informed decision I can make. So even though everything we do in statistics, a lot of it is there's always this chance I'm wrong, that doesn't mean it's not useful, right? I'd like to know if before going to surgery, there's a 95% chance it'll be successful versus a 28% chance, right? Or maybe I don't want to know, but it's nice to know that they can calculate that kind of thing. I love my little brother. Again, I think I brought him up before, didn't I? He would be like, hey, you live or you die, 50-50. I'm like, no, Doc, I want to know you're able to calculate some math stuff. That would make me feel better about everything. All right, did I get all this? I want to save this for later. Take a little picture. Click. Okay. All right. So I like that exercise because it's good practice. It reminds you how to use the one var stat stuff. It's actual data. I think I updated it a year and a half ago, so I think it's time to update it again, but it's actual data from my past courses, so that's always nice. Okay. So, on the other side of this Oh, shit. Don't, let's do this. Don't quite start reading that yet, okay? When yes?
Remember how you said there's a different way to solve it if they give you the sigma and
Not a different way. Here, what was the only standard deviation we knew? S.
yeah.
So I have to use a T. If I knew S and sigma,
You use the z-score.
I use the z-score with the sigma, for sure. Because when can you calculate S? Any damn time you have a sample. But if I know sigma going into a problem, I'm not going to use S. Because it's just an approximation. Okay. All right, so what we're about to get into is really kind of cool. This horrible example I used to use, but a more neutral example is, let's say that this lumber company says that they can cut all this wood really fast, and they would cut it to a mean of 40 inches, right? So they're trying to show off how they can do it really fast, and they can be very precise. And I'm like, all right, let me test that claim. Let me test that claim. How would we test the claim? So this lumber company, I have no idea why I picked lumber company and cutting wood, but oh well, too bad. They can chop this wood down to 40 inches, right? How do we test the claim? Would it be for a side example, if somebody said they were really good at basketball, and you said, all right, took a shot and they missed it, is that enough evidence that they're bad at basketball? No. So if I let them cut one piece of wood and it came off from 40, is that enough evidence that they suck? No. So I have to take a sample of stuff, right? So if they claim that they can cut, starting to go. They can do an average of 40 inches. That's their claim, right? And I take a sample. How big of a sample are you going to take? Which one is going to work best? 10? Why is 10 maybe not the best?
Does it need a bigger sample?
Yeah, I need it how much at least?
420, 35?
20's not good again? I've got to be above
30.
30. So let's make it 35, sure. You guys with me? If I just tell you this, let's say I get a sample mean of 39.2 inches. Is that enough evidence to say that their overall average is not 40? So they're claiming they can cut this to be 40 inches average. If we take a sample of 35 and we get that average, is that 40?
No.
No. But is that by itself enough to say that the average of all the wood they cut is 40 or not?
Yeah.
What if I also told you the standard deviation was 12?
No.
All right, and that's its own problem, ain't it? All right, so I want you to remember, you cannot tell if two numbers are different in statistics without knowing what the standard deviation is. That's what tells me how far apart things are, right? So is that very far from 40? No, especially if the standard deviation was 12. What if the standard deviation was 0.9? That's quite a bit further away from 40, but still not bad. Now what we haven't done, though, is we haven't changed this to be for a group of 35. But the only thing I don't want to get too deep in the weeds with this example. I just want to give you a flavor of what we're doing. We have a claim somebody makes. I take a sample to check it out. That's what gets us into this kind of problem. So let's look at this handout. When I learned this hypothesis test, there were 8 steps, so I've whittled it down to 5. I created this handout back when Sarah Palin and John McCain were running for president, and there was like Joe the plumber or something. So most of my younger people here probably know Sarah Palin. You guys know Sarah Palin? Yes? Okay. Tina Fey and Sarah Palin, I'm not sure if they're Oh, there you go. Okay, a few. Okay. All right. So read through the first little paragraph here. Familiarize yourself with the backstory. Okay. So can somebody explain to me, what I always get is, I always get a student who's like, why do I do any work? The 8.65 is bigger than 7.25. I'm done by Mr. Waller. Why is that bullshit? Why? What part of this says you can't do that? Where did the 8.65 come from? From a sample of 41.
Yeah.
How many coyotes are? I don't know. Probably a lot more than that. So the reason we have to do this whole thing is that the sample, I know it's not going to be the same as the actual average. I already know that. So in order for it to be evident, in this case, what is my claim? What's Phil's claim? What's he claiming? That they live longer, which make it more mathematical. That means that he thinks the mean is bigger than 7.25, right? He thinks that they live longer in captivity than in the wild. So it's the mean age in captivity, the mean lifespan is greater than this. So that's how I can write, way to go longer, don't you? The claim is mu greater than 7.25. So that's your first step, is just find the frickin' claim, because that's what gets things going. If there is no claim, nothing to do. I got nothing to test, so there will always be a claim. So 8.65 is definitely bigger than 7.25, but something I'm going to say a lot when we do these problems is it has to be bigger enough. So help me out here. What if oh yeah, you got to be everywhere, shit. So for this problem, here's 7.25, and really the question is how far away is 8.65, and that distance depends on what? Standard deviation. So I'm going to calculate the distance that this is away from here. Now, where did unusual start before? We're finally to the point where we're going to be more specific about unusual. What's the general sense of unusual? It starts about how far away? 2 steps away, right? Somebody help me out. What does that mean? What percentage is in here, this little tail here?
2.5.
Roughly. Yeah, why? Because within 2 there's 95. Must be 5% outside, or 0.025 here. So there's a symbol I haven't shown you yet. So there's 0.025 here also, right? You guys with me? A little bit? So there's a symbol, it looks like a little fish dude, right? I mean, you know what Greek letter that is? I am the blank and the omega. The alpha, right? So this is a little alpha dude. Alpha is the area in the tails or tail. If it's 2 tails, it's both tails. If it's 1 tail, it's the area in that 1 tail. It is, totally. That's why I put a little eyeball in there. Eyeball normally doesn't go with it, okay? But if you like to put the eyeball in there, it's not going to bother me. So alpha is just the symbol that represents the area in the tails or tail, depending on if I have a 2-tail test or a 1-tail test. Can somebody tell me, what does your gut tell you about this problem? Is it a 1-tail or a 2-tail? Why 1-tail? Greater, exactly. The only place where evidence could show up that he's right is up. Does that make sense? So it's a 1-tail test. What would the 2-tail test be? Would be if I think that the age is different. Higher or lower, which is like, I think it's different from this, or I think it's changed. Okay, I like it. If it has directional words like less, greater, we think it's increased, we think it's decreased, that's going to be a 1-tail test. Yes, sir?
So you use that symbol whenever you only go in one direction?
No. Alpha means the area in the tail or tail. So if it was a 2-tail test, it would be alpha equal 0.05. Because that's the area in both tails. If it's a 1-tail test, it's alpha equal 0.025. So alpha tells you the area in the tail or tails. Depending on if it's 1 or 2 tails, yeah. Okay. Is it cold?
Yeah.
All right.
Those like
Yeah, me too. And I got sauce on.
Oh, God.
There we go. It'll warm up for you guys. All right. Some of you guys are not going to like what I'm about to say, but we're going to basically live this for the next few days. This is a huge part of statistics. This is finally where we're seeing what a clinical trial looks like. We think our new medicine makes you feel better quicker. That sounds like a claim. I can take a sample, I can give them the medication, I can compare it, see if it's quicker enough. Maybe? You guys all right? What's happening? Oh, okay. Just tell me. Normally I don't have control, but they didn't lock it, so hey, I have control. That's the heater, yes. That's why it's warm. Okay. Yes, it's the heater, don't worry. Okay. Now, here's the first... Guys, everything we've talked about so far is based on older stuff, right? You guys must agree because it's true. Here's the first really new thing is what I affectionately... Well, the technical term is null hypothesis, alternate hypothesis. They will affectionately be known as the hoes and the highs. And there will be several jokes related to this. And if you're easily offended, you should have probably left the class already. Another book had HO and HA, so that was the hoes and the ha's. Funny in its own right. So here's the thing. Okay, now we said it's a one-tailed test, right? And in fact, we can draw that right now. Where is that tail going to be? Which side is the tail?
Right side.
Why? It's freaking greater. So here's the 7.25. Phil has got to find a sample way out here. So if he found a sample that was like right here, is that evidence that the population is actually different? No. If I take a sample, where do I expect this sample mean to show up? Around the actual mean, right? So we still have to figure out where this line is, but it's the line between not enough evidence and enough evidence. Not only does it have to be bigger, it's got to be way bigger, right? To be evidence. If I said, yeah, I think he's 42 years old and the person's actually 43, you're not going to say, good God, you were wrong, right? But if he actually turns out to be 70, it's like, all right, you were wrong. So it's got to be different enough to be evidence. Maybe. Oh, some of you guys are like, why do I have to do this? So, the statement that always relates to enough evidence to show proof that it's greater or less will be this guy. That's the one that's always related to where the tail is. Therefore, so in here, that statement should be something that says it's equal to this or, around it, right? The one that says it's different from this should be greater or less. It shouldn't be equal to. So that's why the ho, the null hypothesis, will always have an equal sign in it. And the high won't. This is the guy that says, I don't think it's different, really, or it's not different the way you think it is. And the other one is the guy that says, no, I think it is different. So they are opposite statements. So can you tell me, does this have an equal sign in it? No. So where should it go? Here. So if my claim would have been, I think it's at least 7.25, that would have been mu greater than or equal to, that would have been put in the hook. So the real quick way to remember that is the null hypothesis, HO, that's what's called the null hypothesis, must always have an equal sign. And they have to be opposites of each other. So if I put, this has no equal sign, so I'm going to put it right here. That relates to this, right? That totally relates to the picture we made. So what goes here?
What's greater than 7?
What's the opposite of what I put down already?
Less or equal?
Less than or equal to. So, which one could my claim be? Is my claim always H1? No, because my claim could have an equal sign in it. So my claim just falls where it makes sense, and then the other one is the opposite. So this is what I mean when I say, what are the null and alternate hypotheses? I'm going to write two statements. They're opposites of each other. So if I show that this guy looks like he's right, that means that it looks like this guy is wrong. And if I show that it looks like this guy's wrong, then it means it looks like this guy's right. Because they're opposites of each other, right? Okay, you guys look appropriately not excited. Okay. This question is an old question. Can we use z-scores, t-scores, or nothing? So what two things do you have to look for? I pretty much explained it to you, but so you remember, just I've got to make sure it's normal. And either I say it's normal, or the sample size is bigger than 30. So what's the sample size?
41.
Holy shit. So 1, n equals 41, bigger than 30. Check. So that means I can do something. If n was 11, does that mean I can't do anything? No. Read through and see if it says somewhere it's normal. Now what tells me which kind of score I'm going to use, T or Z? What tells me that? Yeah, which standard deviation do we know? Yeah, I made it really, Basically, when we know the population standard deviation, they're going to yell it from the rooftops, because we're not, in statistics, you're not used to that. You normally don't know shit. And here we're like, holy shit, I know the population. Oh, yeah. Sigma known. So I can use what? Z-scores. Pow. So this is, I always kind of run this down. This is what are we talking about? And this is what can we use to talk about it? Okay. Now who remembers what that symbol there means? When you use a computer, it looks more like a little cursive A, but it's really a goldfish, we know. What does that symbol mean? Alpha, that's the name of it. What does it represent? Area in tail. And where's my tail? Right there, right? So, I've already drawn you a little picture here. How much is in here?
0.05.
No, come on. We could do better than that. 0.01. Are there two tails that I have to distribute it between? No, all of alpha goes right there. There's only one tail. So I put all of alpha in there. If there were two tails, I'd have to cut it in half. But now look, it makes sense now why this is set up the way it is. So before, 2 up and 2 down, 2 standard deviations was always what we consider unusual. But I don't know if you guys remember, I think I did speak about if you work in a nuclear reactor, right? You're going to get off your ass before it gets to 2 standard deviation. You're going to be like, it's 1 standard deviation. What the shit? Or it's in the yellow? All right, shit. You're not going to go, I'm going to wait till it's almost red. You know? I don't think you would. I don't know. If you would, don't work in a nuclear reactor. So now watch. This is too beautiful to believe. Is it going to be positive or negative z-score? Positive, because it's up here. And if it's 0.01, how many tails?
41.
How many tails? 1 tail. 1 tail. 0.01. Oh my God. So this is set up for hypothesis tests. They're going to tell you alpha. These are alphas. If it's 1 tail, you find it up here. If it's 2 tails, you find it down here. Kabam. So what did I say? Yeah, 0.01, 1 tail. So everybody see it's going to be this column here. Do you guys see that? It's even better than confidence intervals. These are alphas. And hypothesis tests are going to tell me what alpha is. So if it was alpha 0.01, but it was 2 tails, I would have looked here. But since it's 1 tail, I'm here. And why am I looking at this crazy t-score chart? Didn't we just say I could use z-scores? Because at the bottom, there's these 2.326. So that is the definition of unusual for this problem. So I'm going to have like an alpha given to me in these problems, and that identifies specifically what unusual is. So if it was a nuclear reactor blowing up problem, it would be alpha 0.10. So it'd be like 1.282. You'd get off your ass quicker. If it's like not a big deal, if you make an error, then it's going to make alpha really small. So you're way out there. Okay. So, all right. This z-score is 2.326. All right. What time we got? Okay, almost there. Let me just say one more thing. I think we're going to head out. So the idea is, if I, in the next step, do you see how I'm going to have use the sample information? I'm going to get a z-score from the sample information. I'm going to see, did it get here? So it's not far enough away to show evidence. So I can't say that, yeah, it looks like it's greater. Or it's going to be here, which is going to be evidence that something's changed. Because what's the probability that something shows up in here if this is the real mean? 1%. I really want this to make sense. There's only a 1% chance for a sample to show up in here if that really is the real mean. If the real mean is higher, like this dude thinks, then if it shows up here, that shows evidence that it is higher. There's only a 1% chance it's going to show up here if that's the real mean. So if it shows up here, it's more likely that's not the right mean. It's more likely that the picture looks like this maybe, moved over. Okay, that's just groundwork, guys. Don't freak out. I mean, there's a lot of groundwork to go over here. So we're getting into chapter 9. That's what this is. That's enough for today, I think. Don't forget your IDs, please, your guys. Give me my calculators. It was right here for a second. Okay, sure. Alright. What's up?
Okay, so your claim is always going to be
The claim, yeah.
I see how you solve the problem and then I understand it. So, okay, and then HO, I think is basically about 17%.
Okay.
Well,
So does the
HO,
claim
H1.
have an equal sign?
No, because
So it's going to be
telling you-
H1.
Yeah, it's only telling you greater.
And then wherever you put the claim, the other guy's the opposite of what I just put down.
Yeah.
So it's the opposite greater than, less than, or equal to.
Yeah, because the claim is saying he wants it bigger than 7.
So if the claim would have been, greater than or equal to 9.
That's the claim?
Yeah, if that was a claim, does that have an equal sign in it?
Claim is greater to or equal to 9.